Alright, so this video is just about the 4 operations with complex numbers, and the syllabus requires you to be able to add, subtract, multiply, and we're also going to divide them. But before we get into that, we're just going to first talk about the equality of complex numbers. Hopefully a lot of this makes sense. We say that 2 complex numbers are equal, so just say Z and W, if their real parts are equal and their imaginary parts are equal. So that's just this language here. So if I look at 2 examples above, if A and C were equal, that's the real parts, and B and D were equal, that's the imaginary parts, then the 2 complex numbers would have to be equal. So here's an example which tests your understanding of that, and it says x plus iy multiplied by 2 minus 2i equals 5 minus 6i, and we need to solve to find x and y. And the first thing I'm going to do is multiply out that right-hand side of that bracket. So that gives me 2x minus 2xi, and then we've got 2yi. And then hopefully you're getting better at this. When I multiply, we get minus 2y first from the minus 2 and the y, but the I times I is minus 1, so that turns this term positive. And then we've got 5 minus 6i. And I'm just going to make sure you understand that we've got here a real part and we've got the imaginary part. And similarly, on the left-hand side, we have a real part here with the 2x and the 2y. And the imaginary parts, well, that's minus 2x plus 2y. So I'm going to rewrite this into the form real plus imaginary. And I'm doing that because this often happens in questions, more complicated than this one, where you have to write it in that form and then you equate parts. And that's what we're about to do. We can now say that, well, this real part must be equal to 5. So 2x plus 2y. And that's only because the 2 complex numbers are equal. And this imaginary part over here must be equal to minus 6. So that gives me 2y minus 2x equals minus 6. And then we're now hopefully in some basic simultaneous equations. So I can tell that these 2 terms are the ones that I can eliminate, and I can do that by adding, because 2x plus minus 2x gives me 0. So when I add the 2 equations, they cancel, and I'm left with 4y equals minus 1. That means that y is minus a quarter. So I've now solved to find y. I just need to find x, and I can do that by substituting the y, which is minus a quarter. I'm just putting it back into equation 1. And that gives me 2 lots of minus a quarter is minus a half. Adding it over gives me 5 and a half, which is 11 on 2. And dividing by 2 gives me 11 on 4. All right, next we're into adding and subtracting complex numbers. And here's an algebraic example of how you add complex numbers. You add their real parts and you add their imaginary parts. Okay, and the same thing for subtracting. You subtract the real parts and you subtract the imaginary parts. So you, I think, could probably pause the video at this point and try and add and subtract the complex numbers and check that we both get the same answers rather than just watching me do it. So what's that? 3 minus 2i. W is 1 plus 5i. That should give you 4 plus 3i. And Z minus W. That's 3 minus 2i minus 1 plus 5i. Please don't make any mistakes with the negative numbers here with the bracket. If you need to, take that extra line, because I often find this would be a question, say, right at the beginning of an assessment task, and you don't want to lose the 1 mark on that question. All right, multiplication of complex numbers, we just use FOIL. So if we think back to year 9, when we did FOIL, first outside, insides last, we'd get AC, ADI, and then I'm going to take the IB and multiply it by the remaining terms in the second bracket. So that gives me BCI, and then this is the only tricky one that you're not used to, which is the I times I again. It's going to give me minus BD. Now, we haven't talked about this little symbol here. This Z with a bar on top of it is actually called the conjugate of Z. And all that means is the imaginary part changes sign. So if your imaginary, so just say you have a complex number of minus 5 plus 7i, then Z conjugate would be minus 5 minus 7i. It is only the imaginary part that changes sign. It does not matter what the real part is. So the conjugate just means change the sign of the imaginary part. So if your complex number was 1 minus 8i, then Z conjugate would be 1 plus 8i. So I've written it here as a plus ib, a minus ib, and when I multiply out, what I want you to notice is we're going to get a squared, and we're going to get minus, so I've got the a squared, then I've got a minus abi, then I've got plus abi, and then once again, now this is what's interesting this time round is I've got the I squared, which gives me minus 1, but I have this additional minus here. That makes a plus, and then a b squared. And these terms clearly cancel out, so in the end I'm just left with a squared plus b squared. Now, this is called a difference of two squares, but what I want you to notice is because we now have the i's in the second part of the bracket, with a difference of two squares, when it's real numbers, we would have always said that a plus b, a minus b, well, that's a squared minus b squared. This is for real numbers. Yeah, but now when we have a complex number, we can see that it actually is a squared plus b squared. And the reason why that happens is when you square the I squared, so this I here and this I here, you're always going to get an additional minus, and combined with that minus there gives you a plus. So we have a new rule for a difference of two squares. So pause the video, and I'd like you to multiply both of these sets of complex numbers. Over here I've got the difference of two squares. Hopefully you can see that. And let's check our answers once you unpause. Okay, and then here I hope you can go straight to 9 plus 4, because what I want you to notice is this is my A and this is my B. So there's no need to be doing FOIL. Okay, so do not FOIL on this expression. Just go straight to 9 plus 4, and hopefully at some point you'll just do that straight in your head and get 13. All right, the last thing we're going to do is divide a complex number, one complex number by another. And when we were in year 9 and we did surds, we learnt about something called rationalizing the denominator, and that's where we're trying to make the denominator a rational number. So if you remember, we multiply by what was called the conjugate, okay, on the bottom, and we used that terminology when we did surds. And so if I look at the difference of squares, two squares here, we get on the bottom 2 minus 3, and on the top we get 2 plus root 3, and the bottom is now, the denominator is now rational. Now, with complex numbers, we're not going to rationalize the denominator. We're going to do something called realizing the denominator, and that just means making the denominator a real number. Now, I want you to notice that when we multiplied a difference of two squares, the conjugate, when we multiplied a complex number by its conjugate, did you notice that we got a real answer? So the way that we realize a complex number, so just say that we've got this complex number here of w over z, the way we do that is we multiply the denominator by its conjugate. So if you look at what's going to happen here, this denominator on the bottom, we've got a difference of two squares, and that's going to become c squared plus d squared. And on the top, of course, I can just FOIL. I can do FOIL, so I'll get ac minus adi plus bci, and then, of course, I'm going to get the plus again. Whoops, lost my page. Sorry. I'm going to get plus BD. Now, I want you to think about what we're doing here. We are just realizing the denominator. So if you look at the denominator now, well, if my complex number, if I look at this complex number over here, can you see that C is the real part of Z and D is the imaginary part of Z? But C and D are both real numbers. So when we have a complex number, just say, for example, Z was 5 minus 6i. That's the real part of Z, and minus 6 is the imaginary part. So the real of Z is 5, and the imaginary part of Z is minus 6. These are both real. I know they belong to a complex number, but the real part and the imaginary part are real numbers. So that means that my denominator here, the c squared plus d squared, is real. Okay, this belongs to the real numbers, which means I have realized the denominator. So let's practice that here. I've got 1 plus 5i on, actually I'll write it down here. So remember, we're going to take my denominator and we're going to multiply by its conjugate, which in this case is 3 plus 2i. And whatever I do to the bottom, I do to the top. So really, I'm not changing the complex number. I'm just multiplying by 1. So this thing equals 1. Okay, let's do that. So on the top, I'm going to FOIL out that expression, and hopefully this is getting quicker for you. Oops, sorry. So we're going to get 1 times 3, 1 times 2i, 5i times 3, that's 15i, and then 5i times 2i, that's going to be minus 10. And on the bottom, we've got the difference of two squares. That's going to be 3 squared plus 2 squared. And so on the top, we end up with minus 7 plus 13i. And on the bottom, we get 13. And I'm going to write it separately. Oops, that shouldn't be that. That should be a 2i plus 15i is 17i. So that's going to be a 17i. Okay, and the reason why I wrote it separately like that is because I like to leave my complex number in the form a plus ib, so I can see the real part and I can see the imaginary part. It's not wrong if you put it all over 13, but that's just my preference. And then over here we can realize, well, this is pretty easy. I hope you can see that to make the denominator real, I would just times by I. And if I times by I on the bottom, I times by I on the top. So that gives me I, and then I squared on the bottom gives me a minus 4, and that is real. So remember, the goal is to get, where's my pen's gone? Sorry. The goal is to get a real denominator. So if I look over here, I've done that there, and my denominator here is real as well. So I have realized the denominator. How much is left? A little bit more. All right, this question's a little bit tricky. I'm actually going to leave it for you to do, but I want to give you a hint. So if you don't want a hint, pause here so you don't receive too much information. But the hint that I will give for you if you do struggle is I would write this. I would split it up into the power of 5 on the top. I would break that into a 2 and a 3. And then on the bottom, I would leave that as is. Now, the reason why I've done that, if you're wondering why is that happening, is I'm going to group those together. And the way that I'm going to group them is I'm going to write it as 2 plus 3i and 3 plus 2i, all cubed. Because if the top and the bottom are being cubed, then I'll just write it as all cubed. Now, the reason why I did that is I'm going to take this expression and realize it. And once you realize it, you'll understand why I bothered to do that, because it actually cleans up really nicely. So what I want you to do, I'm not going to do the rest of it on the video, I want you to give it a go, is realize the pink expression and then cube it. Don't forget there's a cube here. Expand out this bracket and then clean it all up. And I hope that you get the answer that's on your page, which is down the bottom. All right, last little thing we're going to do is we're going to prove two basic identities. Now, I've written here basic identities, but I should also write useful, because these come up all the time, and they may not come up right now, but they do come up all the time. And the first one is that if you add a complex number and its conjugate, you get 2 times the real part of the complex number. So just say I let my complex number be a plus ib, or I could have let it be x plus iy. Just make that look like a plus sign. Let's see what happens. So we've got, I always start with the actual left-hand side, and I've let my complex number be a plus ib. That's just a general form. It could be any number, I know, but I'm making it general. The conjugate will then be a minus ib, and you can see what happens. Hopefully this is nice and obvious. It's just a very simple proof that the imaginary parts cancel, and then I end up with 2 lots of a, and well, a is 2 lots of the real part of z, which is my right-hand side. And the proof of the second identity is very similar. I'm going to go back to using z being a plus ib. So then we're going to have z minus z conjugate, which is a plus ib. Sorry, my brain's going here. A plus ib minus a minus ib. And then I'm going to take the care to expand that minus out so I don't mess up this positive here. Then I can see the imaginary parts cancel. The imaginary parts don't cancel. Let me take that back. I can see that the real parts cancel, and I'm left with 2ib. And don't forget that the 2 and the b, well, that's just 2 lots of the imaginary part of z. So I can write 2 imaginary of z, but don't forget this I. I'll just put that there, which is my right-hand side. All right, last example. This is about making sure you can extract the imaginary and the real part of a number. If you think you know how to do this, definitely pause the video and give it a go. it says here, find the imaginary part of 4i minus z. What I might do first is find out what 4i minus z is. So z, they've told me, is a plus ib. If I expand the brackets, I get minus a minus ib. And remember, I'm going to write this in the form real plus imaginary. It's a really good habit to get into where you understand how to put the real part first, followed by I lots of the imaginary part. And then from there, I think it's really easy to extract just the imaginary part. The imaginary part is the part that's connected to the I, which is this pink bit here. And then here it says the real of 3iz conjugate. So, well, I'm going to first work out what 3iz is. So I've got the conjugate bar on top because I haven't found that yet. I'm going to expand that bracket. That gives me this. And then remember, when I take the conjugate, it means I've got to change the part of the imaginary sign. So I'm going to not put the conjugate bar sign now, but I'm going to write this as 3ia with a minus. So I want you to notice what I've done is taken this term and I've changed it to a negative because we're taking the conjugate of that complex, or we're finding the conjugate of that complex number. And then I've got real, I want to find the real part of this. So I've now found conjugate 3iz. So the real part, well, it's just sitting here because I'm getting into the habit of writing real first, followed by imaginary. So just list down or write down what the real part is. All right, that's video 2 for today.